In this video, we're going to take a deep dive into the various kinds of radioactive decay. Before we actually talk about the different ways that atoms can break down and what they release, it's important to know that radioactivity itself has a few rules. And these rules are basically just 5 conservation rules. So here they are. Any kind of radioactive decay has to abide by the law of conservation of energy and mass. That means that if you add up all the mass and energy of the parent atom, nucleus, and you add up all the energy released and mass of the daughter nuclei, then they have to be equal to each other. Okay? So it has to conform to conservation of energy and mass. It also has to conserve linear momentum, right? So in other words, if a nuclei breaks down and one part of it goes this way and another part of it goes this way, the sum of the momentum before and the sum of the momentum after have to be equal. It also has to conserve angular momentum. So if there's any kind of rotation happening and things break off, then when you have these daughter molecules, that angular momentum must be conserved as well. And it also has to have a conservation of charge. So the net charge of the parent nuclei must equal the sum of the charges of the daughter nuclei. And lastly, there must be conservation of nucleon number. So the total number of nucleons before the breakdown must equal the total number of nucleons after the radioactive breakdown. Got it. Those are all the conservation laws. Radioactivity has to abide by all those. If you ever get a question on the MCAT or any other test that shows some sort of radioactive breakdown and it breaks any of these rules, charge, nucleon, energy, then you know that is not allowed. Okay, just want to get that out. All right, the first major kind of radioactive decay is called alpha decay. And alpha decay is just a radioactive decay that releases an alpha particle. Okay, so when a nucleus disintegrates and produces alpha rays, it is said to undergo alpha decay. Experimental evidence shows that alpha rays are high velocity, and actually what it is it's a helium nuclei, right? It's 2 protons, 2 neutrons. And a classic example of alpha decay is classic uranium radioactive breakdown, which really goes from uranium as the parent nuclei to thorium, which is one of the daughter nuclei, and then the alpha particle itself, which is helium, a helium nuclei. All right. And now let's take a look at how much energy would be released in that radioactive decay. And so this little breakdown here says that when uranium is a parent, then the mass of it is 238.0508 U, where U is the mass of 1 proton. Right, so this is a little bit of a abbreviation notation. So U is just going to be 1.67 times 10 to the minus 27 kilograms. That makes it a little bit easier, right? And so this is going to break down into thorium, which here it says 234.0436 U, plus helium, which is 4.0026 U. Okay? So, and it also explains that the sum of this is 238.0462 U. All right. Notice this is a little less than this. That difference between the two is the mass defect. So delta M is going to be 238.0508 U minus 238.0462 U. Okay? If you go ahead, put that in your calculator, take the difference, multiply by 1.67 times 10 to the minus 27 kilograms, and you'll get your mass defect. And if you take that then and multiply by c squared, you should get, and tell me if I'm wrong, but you should get a value of 6.87 times 10 to the minus 13 joules, and that is approximately the energy released as a result of this radioactive decay. Make sense? Okay, so I hope you're getting the hang of this. There's always going to be some mass difference between the parent nuclei and the daughter nuclei. That difference in mass times the speed of light squared is the binding energy or the energy released in the process of that radioactive decay. Okay, all right, that brings us to the next kind of radioactive decay, which is called beta decay. And maybe you learned about this in chemistry as well. But in beta decay, you're not really losing an alpha particle or a nuclei from the decay process. You're actually losing a high energy electron. And that high energy electron is called a beta particle. Okay? So beta rays, which are the most common radioactive product, consist of negatively charged high energy electrons, and it is actually the weak nuclear force which governs this process. Okay? All right. So, for example, we want to look at the energy release when thorium beta decays here. Okay? So we have this case where we have thorium, which is 234.04359 U, becoming PA. What the heck is PA? PA. Look it up and let me know what it is. All right. Plus the electron. These together have a mass of 234.04330 U, right? Notice this is slightly less than this. True story. Which means if we find the mass defect between the two, the delta M, we just take this 234.04359 minus 234. Notice this is much less energy released because you're not losing a whole nucleus, right? If we find that mass defect and we set that mass defect into Einstein's equation, then we get an energy release in this beta decay of something a little bit smaller, 4.36 times 10 to the minus 14 joules. Okay, go ahead and check my answer on that. But now you're kind of getting the hang of this. Once again, you have this parent mass and these daughter mass. Find the difference, you get a mass defect, multiply that by c squared, you get the binding energy or the energy released in the radioactive decay. All right, there's one other major type of radiation, and that is gamma decay. The nucleus, like the orbital electrons, exists in discrete energy states. So the nucleus itself has quantum states just like the electrons do as they orbit, okay? So when a nucleus changes from an excited state, which is usually denoted by the asterisk, you can see it in the sign here, to a lower energy state, a photon is emitted. That photon happens to be in the gamma spectrum of the electromagnetic spectrum, and you actually release this gamma ray, right? So this is not a material particle. In this case, you're just releasing energy in the form of electromagnetic radiation in the gamma regime of the electromagnetic spectrum, okay? So with nuclear energy levels, however, the photon has a much greater energy, hence a gamma ray, and that gamma decay process is followed. So it shows this example here of it happening in this picture. Okay, so that is a summary of the three major types of radioactive decay. You have alpha decay, beta decay, and gamma decay. And in the case of alpha decay, you have a whole helium nuclei being released during the radioactive breakdown. In the case of beta decay, you just have an electron being released, a super high energy electron. And in the case of gamma decay, you have an actual photon being released, a very high energy photon called a gamma ray. Moving forward, we are going to be looking at now the rate at which this decay happens and how we can use the rate at which radioactive decay happens in order to date objects, from historical pasts and know how old certain things are, which is one of the most impressive biomedical applications of this type of nuclear physics.